Imagine you are holding a sniper rifle, and you are staring down the scope at a paper target 1,000 yards away.
Okay, quite the visual to start with.
Right. Now, hold that thought. Imagine you're also a lead engineer at some multi-billion-dollar tech firm training a cutting-edge artificial intelligence to predict global housing prices.
Oh, wow. Okay, a bit of a pivot.
Yeah. And finally, imagine you are a theoretical physicist trying to mathematically prove the forward flow of time itself.
I mean, those are three entirely different universes of expertise.
Exactly. But what if I told you that your failure at all three of these incredibly complex tasks is governed by the exact same mathematical equation?
It honestly sounds like a massive exaggeration, you know? But it's actually the absolute reality of statistical mechanics.
That's wild.
It really is. We are talking about this universal connective tissue. It's this single mathematical thread that runs through disciplines that, on the surface, seem completely unrelated.
And that is our mission for today's deep dive. We are going to unpack a single, seemingly simple mathematical equation known as the bias-variance decomposition of mean squared error.
Or just MSE for short.
Right, MSE. We've got this stack of incredibly dense source material in front of us, and we are going to figure out how this one equation dictates the limits of what we can know about reality.
Yeah, and this material, it really forces us to abandon the idea that math is just, you know, some abstraction stuck on a chalkboard.
Totally. It's not just theory.
Not at all. We are looking at the strict laws governing how we build models, how we predict the future, and basically how we measure the physical universe.
Okay, so let's unpack this. We really need to start with the master equation itself. The core information in our sources introduces this formula.
Right, the derivation.
Yeah. So the expected value of the squared difference between x and t equals the variance of x plus the square root of the difference between the expectation of x and t.
Which is a mouthful when you just say it out loud.
Well, yeah, it really is. Let's ground those variables for everyone listening. X is a random variable, right?
Right.
Meaning it fluctuates, it has a distribution.
Exactly. And t is just, well, a constant.
Right, but I feel like that definition of t is where most people studying this stuff take their first massive misstep.
Oh, absolutely. There is this pervasive, almost instinctual assumption that t has to represent the average or the expected value of x.
Right, like t stands for target, so it must be the mean.
Yeah, but our source material is super explicit here. T does not have to be the expectation of x. The math is completely agnostic.
It can be literally anything.
Right, t can be any constant whatsoever.
Any constant at all. So t could be 0, it could be 1,000,000, it could be, I don't know, the exact temperature of the room you're sitting in right now.
Literally anything. It's just an arbitrary anchor point that we decide we care about.
Okay, so by setting that anchor point, what is the equation fundamentally asking?
It's asking, if I measure the squared distance between my random chaotic variable x and this totally arbitrary anchor point t, what is that total error actually made of?
What are the ingredients of my failure?
Exactly, and the formula answers that by flawlessly decomposing that total error into two entirely distinct buckets.
I really want to walk through the derivation because the source text describes the proof as a rigorous mathematical trick, and it's honestly brilliant.
This is a very neat trick.
So we start with the core expression inside the brackets, which is x minus t.
Right, the internal distance.
Yeah, and the trick involves forcefully inserting the expected value of x, which we'll call e of x, right into the middle of that expression.
So you subtract it and then immediately add it right back.
Exactly. Why does that work mathematically?
Well, the formal term for this in proofs is completing the term, or sometimes just adding 0.
Adding 0. Because you haven't actually changed the total value.
Right. Subtracting a value and adding it back just nets out to 0. But you have fundamentally changed the geometric grouping of the equation.
So now we have two distinct parts.
Exactly. Part A is the internal fluctuation. That's x minus the expected value of x.
Okay, and part B?
Part B is the external distance. That's the expected value of x minus your target t.
Okay, so because the original formula was looking at the squared error, we have to square this entire new expanded group.
Right, you square the whole thing.
And since you listening are probably well-versed in expanding binomials, you know, we get 3 resulting pieces from that.
The classic FOL method, basically.
Yeah. We get part A squared, we get part B squared, and we get the messy cross term in the middle.
Which is 2 times part A times part B.
Right. And when we take the expected value of that whole massive expansion, things just start to crystallize beautifully.
They really do. Let's analyze those surviving pieces. Look at the first piece.
Part A squared.
Yeah, which is the expected value of the squared difference between x and its own mean.
Okay, so what is that in plain English?
By the strict laws of statistics, that is the literal textbook definition of variance.
Yeah.
It just measures the internal spread of the data.
Oh, wow. So the first term just cleanly, perfectly becomes the variance of x.
Just variance, yep. Then we look at the third piece, the part B squared term.
Right. The expected value of the difference between the mean of x and our target t squared.
Now think about this. The mean of x is a fixed number. T is a fixed number.
So we are just taking the expected value of a constant.
Exactly. And the expected value of a constant is merely the constant itself.
Okay, so that third term perfectly survives as just the square of the expected value of x minus t.
Right. And this is what we mathematically define as the squared bias.
Bias squared.
Yes. It represents the fixed, rigid distance between the true average of our variable and the arbitrary target we care about.
So we have variance on one side and we have bias squared on the other.
Yeah.
But that leaves that messy middle child, the cross term.
Ah, yes. 2 times part A times part B.
According to the notes, this is where the entire decomposition succeeds or fails.
It really is. The survival of this whole beautiful split relies entirely on a property called the linearity of expectation.
Okay, let's pause there, because mathematicians throw around linearity of expectation like it's completely obvious. Let's ground it for a second.
Sure.
It essentially means the average of a sum is equal to the sum of the individual averages.
That's
right?
a good way to put it.
Like, if I want to calculate my total average monthly grocery bill, I can find my average spend on produce, add my average spend on dairy, add my average spend on meat, and it just perfectly sums up to the total.
Exactly. And the critical, almost counterintuitive feature of that linearity is that it holds true even if the underlying variables are deeply correlated.
Wait, really? Even if they impact each other?
Yes. You could buy more dairy specifically when you buy more produce, and the mathematical property remains unbroken. The averages still sum cleanly.
That's super weird. But okay, so in our derivation, we apply this linearity to the cross term.
Right. The constant multiplier, that 2 picks, and the constant distance, the e of x minus t, they can both be pulled completely outside the expectation operator.
Leaving us trying to find the expected value of simply x minus e of x.
Exactly. Which is fundamentally asking, on average, how far is x from its own average?
Which is, wait, by definition, that has to be 0.
It is 0. The positive deviations perfectly cancel out the negative deviations.
Because that's what an average is.
Right. So because that core expectation evaluates to 0, it multiplies against the rest of the cross term.
And the entire messy middle piece completely evaporates. It just vanishes into thin air.
It vanishes entirely.
Leaving us with this flawless, elegant formula. Total error equals variance plus bias squared.
No messy leftover terms, no cross-contamination at all. It mathematically proves that these two sources of error are completely orthogonal to each other.
That is deeply satisfying.
And if we take it one step further, consider what happens if our arbitrary target t actually is the true mean of x.
Okay, so if t equals e of x,
Yeah, then the bias term just becomes 0. 0 squared is 0.
the bias vanishes, leaving only pure variance.
Exactly. The formula elegantly collapses right back into the standard definition of variance, which just proves its structural integrity.
Okay, the dry mathematical derivation is established.
Yep.
We proved it. But keeping this purely in the realm of algebra on a chalkboard is a total injustice to how ubiquitous this equation is.
It really is everywhere.
Because here is where the source material gets phenomenal.
Yeah.
It translates this algebra into 3 distinct physical, real-world analogies.
Right. It yanks the formula out of the textbook and forces it into the physical geometry of our universe.
So translating the abstraction into physics, signal processing, and marksmanship, it proves this isn't just some statistical convention.
It's a structural law of reality.
Let's dive into the geometric one first, because I think it's the most visceral for you listening.
Yeah.
The shooting range.
Okay, let's go back to the sniper rifle.
Right. I am holding a rifle. My target, the absolute dead center bullseye, is T.
Okay.
I pull the trigger 100 times, and the bullet holes scattered across the paper target represent the distribution of my random variable x.
And your ultimate goal as a marksman is to achieve a perfect score, which means you need to minimize your total measurement error.
Which is the left side of our master equation.
Exactly. That total error, how far your bullet holes are from the bullseye, on average, squared.
But the equation dictates that my total failure is actually composed of 2 entirely separate physical phenomena. Let's look at the variance of x first.
Right. In this physical space, variance is simply the spread of your bullet holes relative to each other.
Okay, so if my bullet holes are scattered all over the paper in a massive, loose grouping, I have high variance.
Yes. And if they are all tightly clustered together, practically sharing the exact same hole, you have low variance.
In the terminology of measurement, this is what we call precision, right?
Exactly. Precision is strictly a measure of low variance. And notice that precision has absolutely nothing to do with where the bullseye is actually located.
Oh, right. I could be hitting the extreme top left corner of the paper miles away from the center.
But if your cluster is incredibly tight, your measurement system is technically highly precise.
Because it's just a measure of the inherent randomness of the system.
Mm-hmm.
My hand shaking, a gust of wind, a slight variation in the gunpowder load of each bullet.
All the internal chaos. But then we have the second term, the bias squared.
So what is the bias here?
The bias is the geometric distance between the dead center of your bullet cluster, which represents the expected value of your shots, and the actual bullseye, T.
Okay, so bias represents systemic error.
Yes. In measurement terminology, this is known as accuracy.
So if my rifle's scope is misaligned by exactly 2 inches to the left, my entire cluster will center itself 2 inches to the left of the bullseye.
And that rigid systemic offset is your bias.
Okay, I have to push back on this perfect split, though.
Go ahead.
The math says they are perfectly orthogonal, right?
Yeah.
No cross-contamination.
Yes, the cross term evaluates to 0.
But in the physical world, if I'm holding a sniper rifle and I'm freezing cold so my hands are violently shaking, which is high variance, isn't that physical shaking eventually going to rattle my scope and physically knock it out of alignment over time, thereby creating bias?
That's actually a fantastic observation.
Because in reality, these things definitely bleed into each other.
They do over time, and it highlights the boundary between a mathematical ideal and a degrading physical system.
How so?
Well, in the strict bounds of the equation, we evaluate the system at a static, frozen point in its configuration. We assume the parameters, the scope alignment, and the physiological tremor are independent states in that exact millisecond. What you are describing is a real-world phenomenon known as parameter drift.
Parameter drift, okay.
The variance of the physical system is acting as a degradative force on the systemic calibration over a period of time.
Right.
But at any single isolated moment of evaluation, the error you produce is still cleanly divisible into where the scope is currently pointing and how much you deviated from that point on this specific trigger pull.
That makes total sense. So at the exact millisecond the firing pin strikes, my failure is partitioned perfectly.
Exactly.
So if my hand is perfectly still, meaning 0 variance, but my scope is aimed a foot high, I will put every single bullet perfectly through the exact same wrong hole.
Total bias. Pure systemic error.
Conversely, if my scope is perfectly zeroed, so 0 bias, but I am shivering uncontrollably, my bullets will form a giant, wide halo evenly distributed around the bullseye.
And mathematically, the average position of your shots would be dead center.
Meaning I am theoretically perfectly accurate.
Yes, theoretically. But any individual shot is wildly off target because your precision is terrible.
That distinction between precision and accuracy is so vital. Now let's look at the physics analogy, because the text links this equation directly to the parallel axis theorem.
Right, we are moving from probability straight into rigid body dynamics.
Imagine a physical object for a second. Say, a heavy, irregularly shaped metal rod with various weights welded all along its length.
Okay. And the physical distribution of that mass along the rod mirrors the probability distribution of our random variable x.
And the center of mass of that object represents the expected value of x.
Correct.
Okay, so I have this lumpy metal rod, and I want to spin it like a baton.
Well, spinning an object requires energy. And the path of least resistance, the absolute easiest way to spin any object, is always around its own natural center of mass.
Okay, that tracks intuitively.
The inherent resistance an object has to spinning around its center of mass is called its moment of inertia.
Moment of inertia, and in the context of our master equation.
That inherent physical resistance is the variance. It represents how widely the mass is spread out from the center.
So a compact, dense sphere is really easy to spin, low variance.
Yes.
But a long pole with heavy weights on the far ends is incredibly hard to spin, high variance.
Exactly. But what if you don't want to spin it around its center of gravity?
Right. What if I want to bolt one end of the rod to the wall, creating an arbitrary axis T, and spin the whole thing around that new pivot point?
The laws of physics dictate that it will require significantly more energy.
And the parallel axis theorem tells us exactly how much more.
It does. It states that the total moment of inertia around the new arbitrary axis t equals the inherent moment of inertia around the center of mass.
Plus the total mass multiplied by the square of the distance between the center of mass and the new axis t?
Exactly.
Wait, that distance between the center of mass and the new axis? Squared.
Yes,
That is literally the expected value of x minus t squared.
it is. That is the bias term.
That is absolutely mind-blowing. The mathematical equivalence is absolute.
It's perfect. The extra rotational energy required to force an object to spin around a misaligned axis is exactly the bias squared.
So the total energy I put is just the inherent variance of the object's mass plus the systemic bias of choosing a rotational axis that ignores the object's natural center of gravity.
Exactly. It's astounding that the equation governing a spinning chunk of metal is identical to the equation governing your terrible aim at a shooting range.
It's just wild. And the source text brings in a third physical domain: electrical circuits and signal processing.
Right. Let's look at electrical engineering. If you monitor an electrical signal, like a fluctuating voltage moving through a wire over time.
That fluctuating signal is our random variable x.
Yes. And the reference ground voltage, which is typically 0 volts, is your target T.
Okay, so the total power of that electrical signal relative to ground is the expected value of x squared.
And how does electrical engineering decompose that total power?
Any electrical engineer will tell you that the total power of a signal is the strict sum of its AC power and its DC power.
Exactly. And think about what those are. The DC power, the direct current, is the constant average voltage offset of the signal. It's the baseline.
So that baseline offset, that is our bias.
Yes. And the AC power, the alternating current, is the pure zero mean random fluctuation riding on top of that baseline.
And that fluctuation is our variance.
You've got it. Total power cleanly equals AC power plus DC power.
Variance plus bias. It is inescapable.
Completely inescapable.
It's like saying your total failure at a task, or your total energy output in a physical system, or your total signal strength in a wire. It's always cleanly divided into two independent buckets.
The chaos you can't control and the systemic offset of your initial conditions.
And because that cross term evaluated to 0 in our original derivation,
The math proves that adjusting the DC offset does absolutely nothing to alter the AC fluctuation and vice versa.
so you can slide the baseline voltage up and down all day, and the amplitude of the noise riding on top remains perfectly unchanged.
They are physically orthogonal properties. They do not interact.
Okay, we have firmly established that this formula governs physical reality.
I think we've proved that, yeah.
But what happens when we abandon physical objects and wires, and we use this exact equation to try and predict the future using data?
Because the source material pivots hard right here into the machine learning battlefield.
It does. And this transition is where the equation stops being merely descriptive and becomes the absolute theoretical cornerstone of artificial intelligence and supervised learning.
We just have to shift our definitions slightly, but the underlying mathematical ironclad logic remains totally intact.
Let's redefine the battlefield for an ML engineer listening to this.
Yeah.
In this context, X is no longer a bullet hole or a mass distribution.
Right. X is our AI model's prediction.
And it's a random variable because its prediction heavily depends on the random sample of training data we happen to feed it, right?
Exactly. And T is the true label, the actual reality we're trying to predict, like the real sale price of a house.
Okay. And the total equation, the expected value of X minus T squared, represents the model's generalization error.
Generalization error is the ultimate metric in machine learning. It answers the most terrifying question an engineer faces.
Which is, how well will this model perform in the real world on data it has never ever seen before?
Right. And our master equation breaks that future failure rate into our familiar components, bias and variance.
Okay, so if bias in a sniper rifle is a misaligned scope, how does bias manifest in a neural network or a decision tree?
In machine learning, bias represents underfitting.
Underfitting, meaning the model is fundamentally too simple.
Exactly. It lacks the capacity to capture the underlying complexity of the data. It operates on deeply held, rigid prejudices about how the world works, and it just refuses to learn the actual nuances of the truth.
It's like trying to fit a perfectly straight line to a data set that is clearly shaped like a parabola.
That's the classic example, yeah.
It literally doesn't matter if you feed it 1,000,000 data points or 1,000,000,000 data points. A straight line will always be a straight line. It's aggressively ignorant.
It refuses to update its worldview even when the data begs it to. That is the perfect characterization. A high bias model is stubbornly simplistic.
Okay, so that's bias. Now, variance is the exact opposite pathology, right?
It is. Variance represents overfitting.
Meaning your model is too sensitive, too complex, it has entirely too much capacity.
Right. It doesn't just learn the underlying signal. It meticulously memorizes the random noise, the weird outliers, and the chaotic fluctuations of your specific training data set.
I always think of it like a student studying for a history exam.
Oh, I like this analogy.
So a high bias student just reads the syllabus and assumes every answer on the test is George Washington.
Right. Way too simple.
But a high variance student memorizes the exact page numbers, the font size of the textbook, and a coffee stain on page 42, but completely fails to understand the actual historical concepts.
Exactly. And when they take the test, which is the unseen real-world data, they fail spectacularly because the test doesn't ask about the coffee stain.
That's overfitting
The
perfectly.
high variance model creates a bespoke, incredibly convoluted set of rules to perfectly accommodate every single data point in its training set.
But if you hand it a slightly different data set, its predictions just swing wildly.
It has no stable core belief. It is entirely reactive to its immediate surroundings.
Yeah, the source text introduces a harsh reality check right here. It reveals that our beautiful, clean equation actually has a hidden third term when applied to the real world.
Yes, it does. The irreducible error.
Irreducible error.
Because in our pure mathematical derivation, we assumed t, the target, was a perfect deterministic constant.
Like a frozen bullseye.
Right. But in reality, the data we collect from the world is fundamentally noisy. The true label we are trying to predict is actually a hidden, perfect function plus some random, unavoidable environmental noise.
I like to picture irreducible error, like trying to weigh a single feather on a ship in the middle of a Category 5 hurricane.
That's a great visual.
It absolutely does not matter how perfectly calibrated your scale is, which is zero bias, or how incredibly steady your hands are, which is zero variance. The violent rocking of the boat is the irreducible error.
It's measurement errors, hidden variables you didn't even know you needed to track, sheer entropy.
And that environmental noise has its own inherent variance, right?
Yes, usually denoted in the literature as sigma squared.
Okay, so the true comprehensive equation for generalization error in the real world is bias squared plus variance plus sigma squared.
And that sigma squared is a hard floor. No matter how brilliant your architecture is, your error can never dip below the fundamental noise of the universe.
But if the goal of machine learning is high accuracy, why is this always discussed as a trade-off? Why can't I just hire the best engineers, throw massive computing power at the problem, and engineer a model that pushes bias to zero and variance to zero simultaneously?
It's not about computing power. The inability to eliminate both simultaneously is a profound philosophical paradox embedded in the mathematics of learning itself.
A philosophical paradox.
It is the paradox of local experience versus universal truth.
Local experience versus universal truth. That sounds like epistemology. Break down the mechanics of that paradox for me.
Okay, think about it like this. Any model, no matter how vast, only has access to a finite training set.
Right, you only have so much data.
That data set is its local experience. It does not have access to the infinite universe of all possible data.
Makes sense.
If you, as the engineer, demand that the model have absolutely zero bias, you're demanding that it perfectly, flawlessly adapt to its local experience.
Okay.
And to do that, the model must become incredibly flexible and highly complex.
But by granting it that flexibility and forcing it to trust the current limited data implicitly, it inevitably contorts itself to absorb the local noise.
Exactly. And because it has absorbed the local noise, if I evaluate that model on a totally different local data set, it will bend into a completely different, unrecognizable shape.
Its predictions will fluctuate violently depending on which training set it happened to see.
Which means, by driving bias to zero, its variance just exploded.
Can we ground this in a real catastrophe?
Yeah.
Overfitting isn't just a bad grade on a theoretical test. It actually destroys capital.
Oh, definitely. Consider automated real estate pricing models, like the highly publicized failure of Zillow's algorithmic house-flipping venture a few years ago.
Right, the iBuying disaster.
If a pricing algorithm is given too much flexibility, allowing it to factor in hyper-specific local trends, minor seasonal dips, or chaotic bidding wars on specific streets, it drives its training bias to zero.
Because it perfectly explains the past.
Right. But it has absorbed all the noise of a chaotic housing market. When the macro environment shifts even slightly, that highly tuned, high variance model outputs completely irrational purchase prices.
Leading to massive financial losses because it's wildly overpaying for houses.
Exactly. And on the flip side, if you demand that the pricing model have zero variance, meaning it must stubbornly produce the exact same, stable, predictable valuation, regardless of the chaotic local noise.
It must be incredibly rigid.
Yes. It has to ignore the specific nuances of the neighborhoods to maintain its stability.
And by ignoring those nuances to remain stable, it completely fails to capture the true complexity of housing valuation.
Its bias explodes.
So you are forever trapped on a statistical seesaw.
The entire discipline of machine learning engineering is simply sliding the fulcrum of model complexity back and forth until you find the exact sweet spot where the total sum of the bias and variance is minimized.
But engineers don't just sit there and accept the seesaw, do they? The text details specific, brilliant architectural solutions that were invented purely to hack this mathematical formula.
Yes, bagging and boosting.
Let's look at the mechanics of bagging first.
Bagging stands for bootstrap aggregating, and the most famous algorithmic implementation of this is the random forest.
Okay, random forest.
Bagging is an architectural strategy designed specifically to assassinate variance.
How does the mechanism actually work? How do you mathematically kill variance without instantly increasing bias?
It relies on the statistical properties of averages. Bagging starts by acknowledging that a single infinitely deep decision tree is an absolute disaster.
Because it has terrible high variance, it overfits wildly to its training data.
Right. So bagging says we won't rely on one tree. We will create hundreds or even thousands of parallel, slightly different data sets by randomly sampling our original data.
Okay, so you're building a forest.
Exactly. And we will grow a massively complex, high-variance decision tree on every single one of those slightly different data sets.
So now instead of one chaotic model, you have a forest of 1,000 hyperactive, overfitted, highly unstable trees.
Right. None of them have any systemic bias, but they are all individually incredibly unreliable.
But then you average their predictions together.
Yes. If you feed a new data point into the forest, tree 1 might overreact to some specific noise it memorized and predict 100.
And tree 2 might overreact to different noise and predict 50. Tree 3 predicts 75.
Because their errors are driven by random variance rather than systemic bias, the positive errors and negative errors perfectly cancel each other out around the true mean.
The law of large numbers takes over. By averaging independent high-variance models, the random noise just annihilates itself.
You artificially suppress the variance term of our master equation while preserving the beautiful low bias of the deep trees.
That is genuinely brilliant.
That is exactly how it functions. Now, boosting algorithms like gradient boosting or XGBoost that completely dominate predictive competitions attacks the master equation from the exact opposite direction.
Boosting is designed to methodically assassinate bias, right?
Right. If bagging averages chaotic trees, boosting does something entirely different. It starts with an incredibly simple, highly rigid model.
Think of a tiny decision tree with only one single split.
A weak learner. This weak learner has incredibly high bias. It is prejudiced, it's simplistic, but it is very stable, meaning it has low variance.
It makes a broad, sweeping prediction,
Yeah.
and it is mostly wrong.
But here is the genius of boosting. It calculates exactly how wrong that first model was on every single data point. It calculates the residuals.
Okay.
Then it trains a second, equally simple model. But this second model isn't trying to predict the target. It is specifically trained to predict and correct the errors of the first model.
And then a third model is trained to correct the tiny leftover errors of the second model. It's just a sequential chain.
Through iterative sequential addition, boosting slowly and carefully chips away at the systemic prejudice of the entire ensemble.
It slowly drives the bias down towards zero, while heavily restricting the complexity of each new addition to preserve the low variance of its simple building blocks.
The math completely dictates the architecture. You either build parallel chaos and average it to kill variance, or you build sequential rigidity and layer it to kill bias.
It's beautiful. But I want to pivot here because the title of this entire decomposition is the bias variance decomposition of mean squared error.
Right.
Why is MSE the chosen one? What if I'm an engineer and I just decide to measure my model's error differently.
This is a crucial conceptual pivot. The beautiful, clean addition we've been relying on, where total error cleanly equals bias plus variance with zero messy cross terms, is a highly specific mathematical privilege.
It doesn't work for everything.
It almost exclusively belongs to MSE, which mathematicians refer to as the L2 loss function.
Why not use mean absolute error, like L1 loss, just the absolute value of the distance, without squaring it? Honestly, absolute error makes much more intuitive sense to a normal human being.
It absolutely does.
If a model predicts a house costs $300,000 and it actually costs $305,000, my error is $5,000. It's not 25 million squared dollars.
Yeah.
Squaring things just distorts reality.
It makes intuitive sense for a human to think in absolute distances, yes. But mathematically, the absolute value function completely shatters the clean decomposition.
Really?
If you try to run our original derivation, inserting the expected value and trying to split the terms like we did with MSE, you do not get a perfect algebraic equality.
What happens?
You run headfirst into a fundamental geometric constraint called the triangle inequality.
The triangle inequality. Let's visualize that. If I have a triangle, the length of any one side must be less than or equal to the sum of the lengths of the other two sides.
Right.
The fastest way from point A to point B is a straight line. If I go to a third point C first, the total distance has to be longer.
Exactly. And the absolute value function is strictly bound by that geometry. The absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B.
So it creates a bounding inequality, not a clean sum.
Yes. Furthermore, the absolute value function is structurally nonlinear at its origin. Because of that nonlinearity, you cannot leverage the linearity of expectation.
Oh, that magic wand we use to make the cross term vanish.
It fails completely. The cross terms survive. The terms remain hopelessly entangled.
So you can no longer cleanly separate the shaking hand from the misaligned scope. They just bleed into each other mathematically.
MSE is special because squaring terms is inherently linked to Euclidean geometry and orthogonal projection. It allows independent vectors of error to add up perfectly, like the sides of a right triangle in the Pythagorean theorem.
Okay, so L1 loss ruins the clean split. But what about problems where we aren't predicting a continuous number like a housing price? What about classification problems? Like a neural network analyzing an X-ray and predicting, is this a tumor? Yes or no? Don't use mean squared error for that.
No, you use what the text calls a 0-1 loss. You are either entirely right, which is 0 error, or entirely wrong, which is 1 error.
So how does the decomposition work there?
The transition from continuous regression to binary classification introduces the Pedro-Domínguez classification paradox, and it completely upends our intuitive understanding of error.
A paradox. I love these.
The brilliant researcher Pedro Domínguez published a foundational paper generalizing the concepts of bias and variance specifically for the 0-1 classification space, but the resulting arithmetic behaves like it's from an alien universe.
Break down the Domínguez rules for classification for me.
Okay. In a classification problem, your model's main prediction for a specific data point is simply the class it guesses most frequently if you train it across many different random data sets.
Okay.
Bias is defined rigidly. It is 1 if that main prediction is wrong and 0 if that main prediction is right.
So bias is perfectly binary. Your core assumption is either right or wrong.
Correct. And variance in this context is defined as the probability that the model deviates from its own main prediction due to changes in the training data.
Okay, so if my model is highly variable, it frequently changes its mind and overrides its default assumption.
Here is the paradox. If your bias is 0, meaning your model's core assumption is fundamentally correct, then total error simply equals variance.
Okay, that aligns perfectly with our MSE intuition. The more your model fluctuates and deviates from its correct core assumption, the more often it guesses wrong.
But look at what happens if your bias is 1.
If bias is 1, meaning in my model's core, fundamental assumption is completely fundamentally wrong.
If bias is 1, the formula for total error mathematically becomes bias minus variance.
Minus variance.
Or simply, 1 minus variance.
Wait, hold on. It's a paradox. You are mathematically proving that a broken clock is right twice a day, and in a binary system, that's actually a competitive advantage.
You're starting to see it.
You are saying if my internal compass is totally broken and my core assumption is 100% wrong, I am actually better off having a highly variable, shaky hand. Having a hyperactive model actually improves my error rate.
That is precisely what the Domínguez derivation proves.
Think about the implications of that for a second. Let's say I build a spam filter that is fundamentally biased to believe Every single email I receive is an important message from my boss.
A terrible assumption.
Right. And it is a highly stable, low-variance model. It will confidently let 100% of the spam through. My error rate is massive.
Yes.
But if my model is highly variable, basically shaking and occasionally randomly throwing an email into the spam folder for absolutely no good reason,
Yeah.
my overall error rate actually drops.
Because any deviation from a fundamentally wrong assumption is, by definition, a step toward the truth.
That is completely counterintuitive but mathematically flawless, which means the clean additive separation we love so much in MSE is actually a really rare property.
It is incredibly rare. The text notes that generalized clean decompositions do exist in higher-level mathematics, specifically within a broad family of distance functions called Bregman divergences.
Bregman divergences.
They are a class of distance metrics that share the specific convex geometric properties of MSE. For instance, callback-Leibler divergence, or KL divergence.
Which measures how one probability distribution differs from another, right?
Yes, and it's heavily used in training large language models. It belongs to this family. But for the vast majority of standard engineering metrics, MSE remains the absolute gold standard for achieving that clean, interpretable split.
Okay, we have this beautiful theoretical framework, but the source material addresses a massive point of confusion, a dilemma that trips up almost everyone, engineers and students alike.
Yes, the two variances dilemma.
When we talk about a model having variance, what exact physical or digital property is actually varying?
Failing to properly define what is varying leads to catastrophic engineering mistakes. It is vital to distinguish between classical model variance and evaluation variance.
Because they use the exact same word, but they measure entirely different physical realities.
Let's start with classical model variance, which is the variance our master equation has been talking about this entire time.
Okay, let's unpack classical model variance.
To understand it, you have to run a strict thought experiment. Imagine you fix a single specific testing data point. Let's say a specific digital X-ray image of a lung.
Okay, I have an X-ray. The test data is perfectly frozen in stone.
Now imagine you have access to 100 parallel universes.
Okay, sci-fi rules. I'm in.
In each universe, you gather a completely different set of 10,000 historical X-rays from different hospitals to act as your training data.
Right.
You train an identical algorithmic architecture from scratch in each universe. Then you ask all 100 fully trained models to predict the diagnosis for your one frozen test X-ray.
So the test point never changed. The learning algorithm never changed. The only variable in the entire system is the random draw of the training data from the universe.
Exactly. Those 100 models will output 100 slightly different probabilities for that single X-ray. The statistical variance of those 100 predictions is the classical model variance.
So it strictly isolates the model's sensitivity to the training data.
Yes. It asks the question, how much does the internal logic of my model warp and deform when the training environment shifts slightly?
Got it. It's measuring the stability of the learning process itself. Now, what is evaluation variance and why do people get them confused?
Evaluation variance flips the variables of the thought experiment entirely. This time, you freeze the model.
Okay, so I train it once on one data set, and I lock its internal weights and parameters in stone. The model is permanently frozen.
Now you gather 100 completely different test sets, 100 different batches of new X-rays, you run your frozen model on all 100 test sets, and you calculate the average accuracy score for each batch.
Okay, so I will get 100 different accuracy scores.
And the statistical variance of those scores is evaluation variance.
So evaluation variance isn't measuring how stable the model is at all. It's measuring how stable my test is.
Exactly. It measures the reliability of your evaluation metric. It asks, is my test set large enough and representative enough that I can actually trust the accuracy score it gives me?
Wow.
If your evaluation variance is high, it means your test sets are too small or highly skewed. An algorithm might score 95% accuracy on test set A and drop to 65% on test set B, purely due to the bad luck of which images ended up in set B.
But wait, I have to push back here on the practical reality of this.
Please do.
In the real world, as a working ML engineer, I don't have access to 100 parallel universes.
Sure.
I don't have infinite budgets to collect 100 different training sets. I have one CSV file that my project manager handed me. I cannot run the classical variance thought experiment.
You cannot.
So how does an engineer actually calculate or utilize this theoretical variance if the parallel universes literally don't exist?
This is exactly where statistical theory collides with practical engineering. You are entirely correct. We only have the single empirical data set in front of us. But statisticians have developed 3 primary methodologies to cheat this limitation and peek behind the curtain at the theoretical
I
variance.
absolutely love a good statistical cheat code. Walk me through the first one.
The first is bootstrapping. It is an ingenious mathematical method for faking parallel universes.
How does that work?
If you only have one data set of, say, 1,000 patient records, you can simulate drawing entirely new data sets from nature by drawing samples from your own data set with replacement.
Explain with replacement conceptually for the listeners. It means if I have a bag of 1,000 marbles representing my data, I reach in, pull one out, write down its value, and then I put it back into the bag before I draw the next one.
Exactly. You draw 1,000 times, creating a new simulated data set of the exact same size.
But because I replace the marbles every time, some original records will randomly be picked multiple times.
And statistically, a significant portion of the original records will never be picked at all.
They are completely left out of the simulated universe. Is there a specific math to how many get left out?
Yes, the mathematics of limits dictates that as the dataset grows large, exactly 1 over E of the samples will be left out. Roughly 36.8% of your data will be missing from any given bootstrap sample.
That's a huge chunk.
It is. So you do this resampling process 100 times, creating 100 distinct simulated data sets. You train 100 models, and you measure how much their predictions vary on the left-out data.
Oh, wow.
This bootstrapping variance serves as an incredibly robust, accurate estimate of the true classical model variance. And as we discussed earlier, this resampling mechanism is the absolute mathematical engine that makes random forests work.
Okay, so bootstrapping fakes the universes. What is the second cheat code for seeing variance?
The second method doesn't calculate a number at all. It is purely observational. It's monitoring the train validation gap.
Okay, right. In modern deep learning, where models take weeks to train, engineers rarely attempt to calculate a hard numerical value for theoretical variance.
Instead, they just watch the loss curves on their monitors during the training process.
Right. You watch the error on your training data go down as the model learns, and ideally, the error on your holdout validation data goes down right along with it.
But inevitably, if the model has too much capacity, the training error will continue to drop towards zero while the validation error plateaus and eventually begins climbing back up.
And that widening observable gap between the model's flawless performance on the training data and its degrading performance on the unseen validation data
Is the direct physical symptom of variance.
The model has crossed the threshold from learning the underlying truth to furiously memorizing the local noise.
An engineer doesn't need to know that their model's theoretical variance is exactly 0.042. They just see a massive divergence in the loss curves and immediately know. High variance?
The model is overfitting, I need to intervene.
Exactly. I need to add regularization, implement dropout layers, or stop the training early. They use the gap to indirectly perceive the variance.
And the third method?
The third method is the most mathematically pure, closed-form algebra. But it only works for relatively simple, highly constrained models.
Like what?
For ordinary least squares linear regression, mathematicians have explicitly proven that the variance of the model's internal parameters is directly proportional to the variance of the environmental noise multiplied by the inverse of the data matrix.
Okay, that sounds intense.
It's roughly expressed as sigma squared times the inverse of x transpose x.
So there is literally an exact algebraic formula you can just compute on a computer.
Yes. And analyzing the structure of that formula reveals the physical laws of variance. If your sample size, n, gets massively larger, the data matrix grows, its algebraic inverse shrinks, and the variance systematically decreases.
The math definitively proves that simply gathering more data inherently kills variance.
Exactly. Conversely, if the number of features or dimensions you are tracking increases, the matrix becomes statistically unstable, and the variance explodes exponentially.
Oh. This is the mathematical proof of the curse of dimensionality, contained entirely in a single line of algebra.
It is. It dictates everything. Even if we only have one data set, the invisible ghost of the bias variance equation is dictating every architectural move an engineer makes.
It's incredible. We have covered shooting ranges, spinning metal rods, and the limits of artificial intelligence. Now, let's take this mathematical concept to its absolute extreme limit.
The final frontier.
The source text has one final section, and it genuinely feels like the final boss of this deep dive. Let's look at the fabric of continuous time, Brownian motion, and Ito calculus.
This is where the bias-variance decomposition truly transcends model evaluation. It proves that it doesn't just govern human engineering. It fundamentally governs the structural reality of continuous random processes.
We are moving deeply into stochastic calculus.
Yeah.
Let's set the stage carefully for the listeners. What exactly is Brownian motion?
The classical visualization is microscopic particles, like pollen, suspended in a fluid like water. They are constantly, violently being bombarded by smaller, invisible water molecules.
It's getting knocked around from every angle.
Exactly. As a result, their path of movement is a completely random, jagged, infinitely chaotic walk. That continuous random walk is Brownian motion.
And why is that important?
It is the mathematical foundation for modeling incredibly complex systems, from the fluctuations of stock market prices to the unpredictable behavior of quantum particles.
And Ito calculus is the specialized mathematics invented specifically to study and integrate this exact chaos, right? Because standard calculus, invented by Newton, relies on smooth, predictable curves.
Exactly. In standard Newtonian calculus, the fundamental driver of movement and change is the smooth differential of time, dt.
Okay.
But in Ito calculus, dealing with raw chaos, there is a fundamental mind-bending rule regarding the quadratic variation of a Brownian motion.
What's the rule?
The square of its infinitely small random microscopic steps, which we denote as dw squared, is mathematically and strictly equal to the differential of time, dt.
Wait, let that sink in. dw squared equals dt. That sounds entirely paradoxical.
It does.
You are taking a random, chaotic, unpredictable microscopic jump, squaring it, and you're saying it perfectly, mathematically equals a rigid, predictable, ticking clock.
How can squared randomness equal time?
It is one of the most profound realities of stochastic mathematics.
Huh.
And to formally prove that this equality holds true, mathematicians rely entirely on our exact mean squared error decomposition formula.
Okay, let's unpack this carefully. How do we use the MSE formula to prove the physical flow of time?
We set up a macroscopic experiment. We establish a total fixed time interval, let's call it macroscopic t.
Like 1 full second.
Sure, 1 second. We slice that total time into an infinite number of microscopic intervals, denoted as delta t.
Okay.
Within each of those tiny intervals, the Brownian motion takes a random, unpredictable step, delta w. So we have an army of an infinite number of tiny random steps.
Right. We square every single one of those tiny random steps, and we sum them all up across the entire interval.
Okay.
This massive total sum of squared random steps becomes our random variable x. And our target constant, the thing we want to measure against, is t, the total microscopic time.
Okay, so we want to rigorously verify if the macroscopic sum of the squared random chaos, x, perfectly equals the rigid total time, t.
Which means we want to prove their mean squared error is exactly 0.
Ah.
Precisely. We calculate the expected value of x minus t squared. Now, here's a highly technical, crucial detail that trips up almost every student who encounters this, and our source text explicitly highlights it to warn us.
What's the warning?
The summation of the microscopic steps must occur inside the squared brackets of the MSE formula. You evaluate the error of the aggregate sum, not the sum of the individual errors.
Let me push back on that, or at least ask why. Why does the grouping matter so much? Why can't we just look at the error of one tiny microscopic step, square it, and then just sum up all the tiny microscopic errors? Isn't that infinitely easier?
If you try to evaluate the limits individually, you fall into a mathematical black hole called the trap of high-order infinitesimals.
That sounds dangerous.
It is. Let's look at the math of a single microscopic point. The variance of a single squared step, delta w squared, is statistically equal to 2 times delta t squared.
2 times delta t squared, okay.
Now, consider the nature of delta t. It is infinitesimally small. It is approaching 0. When you take an incredibly tiny number and you square it, it becomes vanishingly exponentially smaller.
Right. 0.01 squared is 0.0001.
Exactly. It becomes a high-order infinitesimal. If you evaluate the points individually and take the limit as delta t goes to 0, the variance vanishes to 0 way too fast compared to the linear mean.
The mathematical terms just disintegrate before they can mean anything physical.
So if you look too closely at the chaos, the math just evaporates in your hands.
Wow.
You cannot evaluate the micro. You must sum them into a macro army first. By putting the summation inside the MSE brackets, we create a dynamic antagonism in the limit theory.
What do you mean by antagonism?
Well, yes, the microscopic variances are shrinking incredibly fast. But simultaneously, the number of intervals, n, is growing toward infinity just as fast.
Oh, I see. The irony of tiny shrinking variances is fighting against the infinite growing size of the army itself.
Yes. So let's apply our MSE decomposition to the macro sum. What is the bias?
Let's see. The expected value of the sum of delta V squared evaluates mathematically to exactly n times delta t.
And n times delta t is just the total time t.
Right. The expected value is t, the target is t, so t minus t is 0. The total bias of the macro system is exactly 0.
The bias is cleanly 0. Now let's tackle the variance.
Okay.
The total variance of the macroscopic sum is simply the sum of the individual microscopic variances, so it is n times 2 times delta t squared.
Let's do the algebra on that. N is just total time t divided by the tiny slice delta t.
Exactly. Substitute that in. T divided by delta t multiplied by 2 times delta t squared. One of the delta t's perfectly cancels out.
Leaving us with a macro variance of exactly 2 times the total time t multiplied by one single remaining delta t.
And now, the final step. We take the limit of that expression as delta t approaches absolute 0. What happens to 2t times delta t?
2t is just a constant multiplier. So as delta t goes to 0, the entire macro variance expression safely and predictably goes to exactly 0.
The trap of high-order infinitesimals is defeated. The delta t squared survived just long enough within the brackets when multiplied by the infinite n to form a stable macro term that smoothly vanishes in the final limit.
Wait, to fully understand why this works, the text mentions something else about this infinitesimal trap.
What's that?
What happens to a cross term like a differential of time multiplied by a differential of the random walk, like delta t times delta v?
Ugh. Cross terms in Ito calculus. They are mathematically too light. A term like delta times delta v has a variance scale equivalent to delta t to the power of 1.5.
Because delta v scales with the square root of delta t.
Exactly. And because the power is 1.5, which is higher than 1 but lower than 2, even when you sum it up an infinite number of times, it doesn't have enough statistical weight to fight the limit.
It completely disintegrates into 0.
It lacks the density to survive the infinite summation. Only the squared random walk, the delta v squared term, possesses the exact, perfectly balanced mathematical density to survive the sum and perfectly match the linear forward flow of time.
So what does this all mean when we bring it back to the core concept?
Let's bring it back.
We have proven that the mean squared error between the macro sum of random chaotic steps and the rigid total time t is exactly 0 in the limit.
The mechanism driving the conclusion is the absolute structural certainty of that 0.
Because our master formula explicitly states total MSE equals variance plus bias squared. And by the laws of real numbers, both variance and squared bias are strictly non-negative.
Right. They can be positive or they can be 0, but they cannot be negative.
They cannot cancel each other out to achieve 0.
It cannot.
So if their combined sum is mathematically proven to be exactly 0, the math is forcing a physical reality. It is ruthlessly forcing both the bias to be 0 and the variance to be 0 simultaneously.
And as we established at the very beginning of this deep dive, if a random variable has 0 bias, it is perfectly flawlessly centered on its target. If it has 0 variance, it has lost all its capacity for randomness.
It has collapsed entirely into a deterministic constant.
It is essentially proving that when you zoom out far enough, the infinite sum of total, unpredictable, random chaos perfectly solidifies into absolute predictable certainty.
That is beautiful. The bias variance equation is the rigorous bridge that allows mathematicians to confidently state that the chaos of a random walk squared is mathematically identical to the rigid ticking of a clock.
That is the profound, almost poetic beauty of it. The exact same algebraic decomposition that tells an engineer why their decision tree is overfitting a data set is the exact same mathematical tool used to prove the structural, inevitable fabric of stochastic time.
We have covered an immense amount of ground today. Let's trace the arc of the journey one last time. We started with a basic algebraic trick on a chalkboard, completing the term to miraculously annihilate a cross term,
which revealed that total error in any continuous system is composed of 2 independent antagonistic forces: systemic prejudice or bias and chaotic sensitivity or variance.
We took that abstract formula to the shooting range, proving that accuracy and precision are mathematically orthogonal. We spun heavy metal rods to test the parallel axis theorem. We watched electrical circuits split their total power cleanly into AC noise and DC baseline offsets.
We then entered the modern machine learning battlefield. We saw how models are endlessly trapped on a seesaw between underfitting local reality and overfitting to local noise.
And how complex architectures, like random forests and XGBoost, are explicitly engineered to surgically target and eliminate one term of our master equation.
We discovered the bizarre Pedro Domingos paradox, realizing that in binary classification, a broken compass with a violently shaky hand is somehow mathematically superior to a broken compass held perfectly still.
We untangled the dilemma of the two variances, learning how engineers fake parallel universes using bootstrapping to see the invisible limits of their algorithms.
And finally, we scaled the peak of Ito calculus, utilizing the MSE decomposition to rigorously prove how infinite microscopic randomness inevitably coalesces into the rigid macroscopic passage of time.
It truly earns the title of a master equation. So the next time you make a mistake, a bad prediction in your career, or a flaw in your judgment, you can ask yourself, was it an error of bias?
Was my core assumption, my internal T, just fundamentally flawed from the start?
Or was it an error of variance? Did I overreact to a single chaotic event, absorbing the local noise of my experience?
Understanding which specific mathematical failure you are suffering from completely dictates how you must attempt to fix the problem.
Exactly. Now, to wrap up, I want to leave you with a final lingering question, something to mull over on your own time. Early on, we talked about the irreducible error, the hidden sigma squared.
The hurricane.
Right. We likened it to trying to weigh a feather on a ship in a hurricane. It is the inescapable noise of the universe that prevents any predictive model from ever achieving 100% true accuracy.
It's always there.
If that irreducible noise is an inescapable physical law of reality, does that mean true certainty in any complex system is just an illusion? Is certainty just a convenient temporary fiction we invent in the rare fleeting moments when our systemic bias and our chaotic variance just happen to perfectly accidentally align?
That is a thought that will make you question every assumption you hold.
Keep unpacking that. Remember, the next time you look at a medical diagnosis, an economic prediction, or even just a broken digital clock, the muddy, chaotic waters of reality are always bound by the math. Thanks for taking this deep dive with us.